Object detection, computer vision. But before we get started, hit the like, subscribe, and share this with anyone you know taking the AWS Machine Learning Associate exam. Object detection. This is teaching machines to see and locate. All right. Let's get over here. All right. So computer vision's fundamental challenge extends beyond simple image classification that assigns single labels to entire images. Real-world applications require understanding not just what objects appear in images, but precisely where they're located, identifying individual items on retail shelves, detecting defects on manufacturing lines, locating vehicles and surveillance footage, or finding anomalies in medical scans, right? Object detection solves this challenge by simultaneously classifying multiple objects within images and localizing each with bounding boxes that specify precise coordinates. The algorithm outputs three critical pieces of information for each detected object: the class label, identifying what it is; bounding box coordinates, indicating where it appears; and confidence scores, quantifying prediction certainty. SageMaker provides two distinct implementations of object detection algorithms, each reflecting different deep learning frameworks and offering unique capabilities for custom model development. Okay. So the two paths to object detection. So SageMaker's dual object approach reflects the evolution of computer vision frameworks and provides strategic choices based on project requirements and existing expertise. First is MXNet. All right. So this represents SageMaker's original implementation. It's built on the single-shot multi-box detector, SSD framework, right? So this revolutionized real-time object detection through efficient single-pass processing. The implementation uses convolutional neural networks with either VGG16 or ResNet 50 backbones, providing proven architectures that balance accuracy with computational efficiency. MXNet variants includes comprehensive data augmentation capabilities, flipping, rescaling, and jittering. This improves model robustness without requiring external pre-processing pipelines. Transfer learning supports enables starting from pre-trained weights rather than training from scratch, dramatically reducing training time and data requirements for new detection tasks. The other type, TensorFlow. So this provides access to TensorFlow's extensive model garden. It offers modern architectures like EfficientNet and MobileNet, alongside traditional ResNet variants. This flexibility enables optimization for specific deployment constraints, from edge devices requiring lightweight models to cloud applications demanding maximum accuracy. The TensorFlow implementation model, specific hyperparameters, and training pipelines provide fine-grained control for practitioners comfortable with TensorFlow's ecosystem. While more complex than the streamlined MXNet approach, this flexibility enables advanced optimization strategies that extract maximum performance for available training data. Okay, let's see. Okay, so understanding some of the architecture, right? So both implementations build upon convolutional neural networks that learn to extract hierarchical visual features through backpropagation. Early layers detect basic visual elements like edges and textures, while deeper layers combine these into higher level features representing object parts and eventually complete objects. The single-shot multi-box detector framework processes images through these CNN backbones, generating predictions at multiple scales simultaneously. This multi-scale approach enables detecting both large and small objects within the same image, a critical capability when objects vary dramatically in size, from distant vehicles to nearby pedestrians and autonomous driving scenarios. Transfer learning leverages that insight and the visual features learned on massive data sets like ImageNet transfer efficiently to new detection tasks. Rather than learning edge detection and textual recognition from scratch, pre-trained models provide robust starting points that require only fine-tuning on domain-specific detection tasks. Okay, let's go into a little bit of data prep. All right, so object detection supervised learning demands careful annotated training data where each image includes precise bounding box coordinates and class labels for every object of interest. This annotation process requires more effort than simple image classification, but enables the rich spatial understanding that detection applications require. For MXNet implementation, You prepare images in a standard JPEG or PNG format and create corresponding JSON annotation files describing object locations. So it'll be something like the image size, the bounding box ranges, and then an ID, right? So each annotation will specify the class identifiers, the bounding boxes using XY coordinates for top left and bottom right corners. And these coordinates will define rectangular regions containing detected objects. This will provide spatial supervision necessary for training localization alongside classification. The TensorFlow implementation requires format-specific preparation depending on chosen backbone architectures, typically involving TF record serialization that packages images and annotations into binaries that are efficient formats optimized for training throughput. So let's jump in the console and get hands on this a little bit. So one, you're going to upload all of your data to S3, right? Which will be this one right here. Okay. You can do it through the CLI, but the GUI is always fine, right? And you can consider transfer acceleration if you want to reduce upload time. So let's go over to SageMaker and console. Go down to training. All right, training jobs. Create training job. All right, let's say computer vision test. All right, IAM role for execution to be able to do this. Your algorithm. All right. MXNet right here. MXNet right here. MXNet right here. Okay. And then do I see TensorFlow? Did they move it? Oh, wow. Did they move it? I think they moved it. Let's see, please. No. I don't see it. Oh, wow. Oh, okay. Let's go for this basic one. I guess they moved it. Well, my apologies. All right. So first thing you're going to do after that, you select your input mode, pipe or file. File, downloads it locally, then process it. Pipe goes straight from S3 into it. Okay. Select your input type. GPU is typically going to be the best way to go for it. This is computationally intense. All right. So something like ml.p. These will be accelerated compute. You have some very large ones down on the bottom. Basically, intensity in the compute carries with it. All right. And you can select all of this. For large models or massive data sets, you can do the extra large, the 24 extra large. But these are going to be insanely huge, right? If you're budget oriented, try the G4, right? This will give you accelerating compute and it'll be more cost effective. All right. So you should allocate about 100 gigabytes for data sets with thousands of images. All right. And on your instance count, that'll be good. All right. Next, you said keep alive period, 60 minutes at least. Oh, I'm sorry, at most. My apologies. Your encryption, your runtime. All right. And for network isolation, select the VPC for your organization. Subnets that are appropriate, security groups that are appropriate. Basically isolate this. Make sure nothing can impede and nothing can bleed out. All right. Then you'll go to your hyperparameters. All right. So this will basically give you controls for detection model architecture and learning behavior, right? So let's go for some key hyperparameters. All right, number layers. All right, number, no, that's not it. Number of classes, there we go. Okay, so number of classes, right? So you need to use this to match the number of distinct objects in your data set. This is a fundamental parameter because it must align exactly with your annotation class identifiers to prevent training errors. Okay, set it to 1,000, right? Because we have 1,000, have 1,000 objects. We should have 1,000 here. All right. Then you have your, let's see, your batch size. Since we're doing MXNet, it should be mini batch size. So you do this to balance training stability. It'll be typically between 16 and 64, depending on your image resolution and instance memory capacity. Larger batches, will provide more stable gradients, but they'll require more memory. So let's set this at 48. All right. Learning rates. Okay. So this will control the gradient step. So start with a moderate value. 0.001 would be good. And this will object detection will benefit from the learning rate. Then your epoch right here. This will control the training duration. It'll typically be between 30 and 100. So let's set it to 50, depending on your data set size, right? So monitor the validation metrics to find the optimal range to hit this. And then since we're in MXNet, I don't see it. No, they moved it. Oh. No, they moved it. Okay. And then pre-trained model. Okay, this is a good one. So you can enable transfer learning by setting the use pre-trained to 1, right? So loading a pre-trained ImageNet can provide initial feature extractors, right? So this will reduce the required training data and acceleration, and it'll accelerate the convergence, okay? And then I think we're good here. Outside of configuring your source in S3 and content type, input mode, compression if necessary. If we chose Recordio, then we choose Recordio, but we chose image, so we're choosing image. Your input type, oops. Your input type right here, your checkpoint here, or local file, your output and or local, and or encryption key, right? And then spot training for discounts, and then you click create training job. All right. So when your training is complete, the model artifacts will be saved to your S3, and this will contain the trained CNN weights, detection head parameters, and configuration metadata for inference and operations. All right. And then your application code will be solid for it. So let's hit cancel, because we're not going to make that. It's going to cost. All right. Okay. So how does this integrate with AWS's computer vision ecosystem? All right. Object detection represents one component within AWS's comprehensive computer vision offering, each serving distinct use cases and expertise levels. So there's Amazon recognition, which is the fully managed object detection through simple API calls. This is ideal for applications requiring standard detection capabilities without custom model training. Recognition handles all the infrastructure and model management, enabling rapid deployment but limiting customization. Then you have SageMaker object detection, which offers complete control over training data, model architecture, and detection categories. This flexibility suits applications requiring domain-specific detection, like manufacturing defects, rare medical conditions, or specialized inventory items that generic models can't detect accurately. And then you can also include SageMaker Ground Truth, which will provide data labeling infrastructure to accelerate the annotation. And so it adds that human in the loop workflow that will combine the automated pre-labeling with human review. So you can integrate that with your data prep to basically remove constraints from custom detection projects. All right, and then the biggest thing, cost. So this is showing recognition, which is fully managed, but need to get something up here. So object detection GPUs require a substantial amount of compute, right? So there's cost considerations. So you have to be strategic about your resource planning. When your training costs are working, you have to worry about data set size, model complexity, required accuracy, and the instance costs. And that can be from $1 to $2 to $5 an hour, depending on if you're going CPU or GPU, right? Well, these are GPU, sorry. Yeah, so GPU. So it'll be about $3 to $5 an hour. All right, so you can use spot instances for non-urgent training and achieve a significant cost savings. They say 50 to 90%, but you'll have to do that for your own work. And then the object detection training will support checkpointing that'll enable recovery from the spot interruptions, right? So you won't lose progress, and you could make this a cost optimization for a production scenario. So for inference, You need to evaluate real-time requirements before defaulting to the expensive GPU instances, because many applications tolerate slight latency increases that enable using cost-effective CPU instances, which can reduce your ongoing hosting costs. So you can also consider batch transformations for periodic detection tasks rather than persistent endpoints. And processing daily inventory images or weekly quality control scans can work efficiently through scheduled batch jobs without continuous endpoint hosting. So use this and figure out what works for you for flexibility, for customization, and making sure that the complexity of it doesn't mess with your organization's needs. So that's what we have here for computer vision. Thank you for joining. Remember to hit the like button, subscribe, and share this with anyone you know taking the AWS Machine Learning Associate exam. Thank you, and have a good day.